Have you ever looked up at the night sky and wondered where is all of this going? The stars, the galaxies, even our own Milky Way, they aren't just drifting aimlessly through space. They're being pulled, drawn toward something massive, something mysterious, something we still don't fully understand. Hidden in the depths of the cosmos, there's a gravitational behemoth so powerful it's bending the paths of entire galaxies, tugging them toward an unseen destination. Scientists call it the Great Attractor, and it's one of the universe's most tantalizing enigmas. Picture this: every galaxy around us, including our own, is caught in a cosmic current, racing toward a point we can't even see directly. It's like being on a river swept along by a hidden waterfall just beyond the horizon. The Great Attractor sits at the center of this celestial pull, a region of space with the mass of tens of thousands of Milky Ways packed together. Yet for decades it remained hidden from our telescopes, obscured by the thick dust and stars of our own galaxy's disk. Even now, as we've begun to map its influence, it raises more questions than answers. What is it? Why is it pulling us? And what happens if or when we get there? This isn't just a story about distant galaxies and abstract physics. It's about us, our place in the universe, our quest to understand the forces shaping existence itself. The Great Attractor challenges everything we think we know about gravity, dark matter, and the large-scale structure of the cosmos. It's a reminder that, even in an age of towering telescopes and deep space probes, the universe still holds secrets big enough to humble us. So let's embark on this journey together, peeling back the layers of one of astronomy's greatest mysteries. By the end, you might just see the night sky and our place within it in a whole new light. To understand just how strange the Great Attractor really is, we need to rewind to the 1970s, when astronomers first noticed something odd about the way galaxies were moving. Even after accounting for the expansion of the universe, entire clusters of galaxies, including our own, were being dragged off course as if caught in an invisible current. At first, researchers thought it might be a glitch in their measurements, but as more data came in, the truth became undeniable: this wasn't an error. It was a gravitational anomaly unlike anything we'd seen before. A colossal concentration of mass warping space-time itself on a scale so vast it defied explanation. So what exactly is the Great Attractor? Think of it like the universe's version of a whirlpool, a region where gravity's pull is so intense it bends the paths of galaxies like light through a lens. Nestled about 250 million light-years away in the direction of the constellation Centaurus, it isn't a single object, it's a sprawling web of dark matter, superclusters, and countless galaxies, all packed together in a cosmic knot. The combined gravity of this hidden metropolis is pulling thousands of galaxies, including ours, toward it at staggering speeds over 14 million miles per hour. And yet, we still can't see most of it directly. Here's why that's so frustrating. The Great Attractor lies behind the Zone of Avoidance, a dusty veil of stars and gas in our own Milky Way that blocks our view. It's like trying to study a mountain peak while standing in a fog bank. For decades, this blind spot left scientists guessing. But thanks to infrared telescopes and radio astronomy, we've begun piecing together the puzzle. What we've found is even stranger than imagined. The Great Attractor might just be one piece of an even larger structure, a gravitational domino effect stretching across the cosmos. But here's the twist: we're not just hurtling toward the Great Attractor. The entire local universe, our galaxy, Andromeda, and countless others, is part of a much grander flow, pulled toward something even more massive lurking beyond it. The Great Attractor, then, isn't the end of the journey. It might just be a waypoint on a voyage to something far bigger, a mystery within a mystery that keeps rewriting our understanding of the universe's architecture. Imagine the universe as a vast, flowing river, not of water but of galaxies, each one adrift in a current stronger than any force we've ever known. This isn't just poetic imagery. It's the reality of the cosmic flow, the relentless motion of entire galaxies being drawn toward the Great Attractor. Like leaves caught in a stream, galaxies across our local universe are moving in unison, swept along by gravitational tides so powerful they override even the expansion of space itself. Scientists first pieced together this grand motion by studying something called redshift, the stretching of light as galaxies move away from us due to the universe's expansion. But here's the catch: when they looked toward the Great Attractor, they found galaxies weren't just receding evenly. Instead, they were deviating, their paths skewed as if tugged by an invisible hand. This anomaly revealed itself through subtle shifts in the light's wavelength, a cosmic fingerprint of motion known as the Doppler effect. Just as a siren's pitch changes as it races past you, the light from these galaxies shifts slightly as they're pulled toward the attractor, betraying their secret journey. To grasp the scale of this movement, picture standing on a train platform as two high-speed trains pass each other in opposite directions. One represents the universe's expansion, carrying galaxies apart. The other, the Great Attractor's pull, dragging them sideways against that flow. Our own Milky Way is caught in this celestial tug of war, racing toward the attractor at over 1 million miles per hour, fast enough to cross the United States in less than 10 seconds. And we're not alone. Thousands of galaxies, from the majestic Andromeda to the faintest dwarfs, share this fate, locked in a dance dictated by gravity's unbreakable grip. What makes this motion even more astonishing is how coordinated it is. Across hundreds of millions of light-years, galaxies move like synchronized swimmers, their paths bending toward a common center. This isn't random drift, it's evidence of a hidden scaffold of dark matter, an invisible framework guiding the universe's largest structures. The Great Attractor sits at the heart of this web, a gravitational anchor warping the fabric of space-time so profoundly that it redirects the trajectories of entire galactic superclusters. Yet even now, much of its structure remains obscured, leaving us to wonder, what other secrets might lie hidden in this cosmic undertow? The mystery of what's actually pulling us toward the Great Attractor only deepens when we realize just how much of it remains hidden from sight. Unlike a black hole or a bright galaxy cluster, this colossal force isn't something we can point a telescope at and study directly. Instead, its presence is felt through its gravitational grip, an invisible hand guiding the motion of galaxies across the cosmos. So what's really behind this immense pull? The answer likely lies in two of the universe's most enigmatic phenomena: dark matter and the cosmic structures it sculpts. Dark matter, that mysterious, invisible substance that makes up roughly 27% of the universe, doesn't emit, absorb, or reflect light. Yet it exerts an undeniable gravitational influence, acting as the hidden scaffolding upon which galaxies and galaxy clusters are built. In the case of the Great Attractor, astronomers suspect it's not just a random clump of matter but a sprawling supercluster, a dense knot of galaxies, gas, and dark matter woven together by gravity. Picture a city at night. The visible stars and galaxies are like streetlights, but the dark matter is the unseen foundation, the roads and infrastructure holding everything in place. Without it, the sheer amount of visible matter we can observe wouldn't be enough to explain the attractor's overwhelming pull. But why is studying this region so frustratingly difficult? Blame our own galaxy. The Milky Way's disk, packed with stars, dust, and gas, blocks our view of the Great Attractor, creating what astronomers call the Zone of Avoidance. It's like trying to peer through a thick curtain. The very heart of our cosmic neighborhood is obscured by the crowded foreground of our own celestial backyard. For decades, this blind spot forced scientists to rely on indirect methods, mapping the attractor's influence by observing how nearby galaxies move, like detectives reconstructing a crime scene from scattered clues. Recent breakthroughs in infrared and radio astronomy have begun lifting that veil. Instruments like the Hubble Space Telescope and the Atacama Large Millimeter Array can pierce through the dust, revealing glimpses of the structures lurking behind. What they've found is astonishing. The Great Attractor isn't just a single anomaly. It's part of an even larger cosmic watershed, a gravitational confluence where multiple superclusters converge. Some researchers now believe it's a small piece of something far grander, a mind-boggling structure known as the Laniakea Supercluster, a web of galaxies spanning over 500 million light-years. Yet, even as we uncover more, the Great Attractor keeps its secrets close. The more we learn, the clearer it becomes that this isn't just about one cosmic oddity. It's a window into how the universe organizes itself on the largest scales. Every discovery raises new questions. How much of the attractor's mass is dark matter? Are there even larger structures pulling it toward something else? And what does this mean for the ultimate fate of our galaxy? One thing's certain, the universe is far stranger and far more interconnected than we ever imagined. Mapping the Great Attractor is like trying to read a book with half the pages glued together, except the missing pages hide the most critical chapters. The biggest obstacle, our own galaxy, the Milky Way's bustling disk packed with stars, gas, and dust, creates a blind spot astronomers call the Zone of Avoidance. Imagine standing in a crowded train station, trying to spot a friend on the opposite platform through a sea of moving bodies. That's the frustration scientists face when they point telescopes toward the Great Attractor's direction. Light from distant galaxies gets absorbed or scattered by the Milky Way's thick interstellar haze, leaving a glaring gap in our cosmic maps. For decades, this meant astronomers had to study the attractor indirectly, like detectives reconstructing a suspect's face from blurred security footage. They tracked the motion of galaxies around the zone, measuring how their paths bent under the attractor's pull. But without seeing the culprit directly, theories piled up. Was it a single massive cluster, a network of dark matter filaments, or something even stranger? The breakthrough came when NASA, a Wilkinson Microwave Anisotropy Probe, or WMAP, and later the Planck mission, turned their gaze to the cosmic microwave background, the faint afterglow of the Big Bang. These telescopes didn't just look through the Zone of Avoidance, they looked around it, mapping subtle distortions in the primordial light caused by the attractor's gravity. It's like feeling the shape of an invisible object by studying how it bends the air around it. Yet even with these tools, the picture remains incomplete. Radio telescopes like the Parkes Observatory in Australia have pierced the dust veil by detecting hydrogen emissions from hidden galaxies, revealing faint structures lurking behind the Milky Way. Meanwhile, infrared telescopes like Spitzer and Webb see through the cosmic fog by capturing heat signatures rather than visible light. Each wavelength adds another piece to the puzzle, but the attractor's full structure still eludes us. What makes this search so thrilling is what it reveals about the universe's architecture. The Great Attractor isn't just a destination, it's a crossroads. Recent studies suggest it's part of the Laniakea Supercluster, a sprawling web of galaxies that forms our cosmic neighborhood. Mapping it isn't just about solving a local mystery, it's about understanding how gravity sculpts the universe on the grandest scales. Every new observation peels back another layer, showing us that the cosmos is far more interconnected and far more mysterious than we ever dreamed. The challenge now, building telescopes powerful enough to see deeper into the zone, to trace the dark matter threads that bind this hidden metropolis together. It's a reminder that sometimes the universe's biggest secrets are hiding right in our own backyard, masked not by distance but by the very galaxy we call home. To truly grasp where we stand in the universe, we need to zoom out far out beyond the Milky Way, past the local group of galaxies, and into a structure so immense it redefines our sense of place. Welcome to the Laniakea Supercluster, a cosmic metropolis of galaxies stretching over 500 million light-years, with the Great Attractor as its gravitational heartbeat. The name Laniakea comes from Hawaiian meaning immeasurable heaven, and it couldn't be more fitting. This isn't just a random scattering of galaxies. It's a carefully woven tapestry of filaments, clusters, and voids, all bound together by the relentless pull of gravity. And at its center, the Great Attractor serves as the anchor, the focal point where the threads of spacetime converge. Picture the universe as a vast network of rivers, each flowing toward a central basin. Laniakea is one of these basins, a gravitational watershed where every galaxy within its borders, including ours, is drawn inward like leaves swirling toward a drain. The Great Attractor acts as the drain's core, the point where the supercluster's collective mass exerts its greatest influence. But here's the twist: Laniakea isn't static. It's in motion itself, pulled toward an even larger structure known as the Shapley Supercluster, a gravitational titan lying beyond our horizon. This means the Great Attractor isn't just pulling us, it's being pulled too, caught in a chain of cosmic forces that stretch across the observable universe. What makes Laniakea so remarkable isn't just its size, but how it reshapes our understanding of home. For centuries, we saw Earth as the center of everything, then the Sun, then the Milky Way. Now we know our galaxy is just one of 100,000 in Laniakea, a single speck in a sprawling archipelago of stars. Mapping this supercluster required a revolution in astronomy, using not just light, but the motion of galaxies themselves as a guide. Researchers tracked the subtle flows of entire galaxies, like tracing ocean currents by watching drifting boats, to reveal the invisible contours of dark matter that define Laniakea's boundaries. Yet even within this vast structure, the Great Attractor stands out. It's not the densest cluster or the brightest region, but its gravitational influence is unmatched, a testament to the hidden power of dark matter. Think of it as the quiet conductor of a galactic orchestra, unseen but essential, directing the movements of countless stars and galaxies with an invisible baton. And just as a conductor follows the score, the attractor may itself be following the gravitational cues of something even grander, a reminder that the universe's hierarchy of scale has no clear end. This discovery humbles and excites in equal measure. Humbling because it shows how small we truly are in the cosmic web. Exciting because it proves there's still so much to explore right in our own backyard. The Great Attractor and Laniakea aren't distant curiosities. They're our local universe, the neighborhood we're only now beginning to map. Every new observation peels back another layer, revealing how deeply interconnected the cosmos really is. And with each revelation, we're forced to ask, what other invisible currents are shaping our journey through the universe, and where, in the end, are they taking us? The Great Attractor may command our local universe's motion, but it's far from the only gravitational giant shaping the cosmos. Across the universe, mysterious concentrations of mass warp spacetime, bending light and redirecting galaxies like cosmic traffic controllers. Take the Shapley Supercluster, for example, a behemoth 8 times more massive than the Great Attractor, located over 650 million light-years away. While the Great Attractor pulls us gently but persistently, Shapley's gravitational grip is so powerful it might be tugging on entire superclusters, including our own Laniakea. It's like comparing a river's current to the tidal pull of the ocean. Both move water, but on vastly different scales. Yet these two titans aren't rivals, they're part of the same cosmic dance. Some astronomers believe the Great Attractor itself is being drawn toward Shapley, caught in a chain of gravitational dominance that stretches across the observable universe. Imagine a game of interstellar tug-of-war where galaxies, superclusters, and even dark matter filaments are the ropes, and the prizes are the fate of entire galactic neighborhoods. This hierarchy of pull reveals a startling truth. The universe isn't just expanding uniformly. It's a dynamic web of flows and counterflows where gravity's invisible threads weave patterns we're only beginning to trace. But why do these anomalies exist in the first place? The leading theory points to the early universe, where tiny fluctuations in density, seeded by quantum chaos in the first fractions of a second after the Big Bang, snowballed over billions of years. Regions slightly denser than their surroundings pulled in more matter, growing into the vast superclusters we see today. The Great Attractor and Shapley are simply the largest clumps in this cosmic lottery, their immense gravity sculpted by eons of accumulation. Yet there's a twist. Simulations suggest these structures shouldn't be quite this massive. Their sheer size challenges our models of dark matter's behavior, hinting that something fundamental in our understanding of gravity or cosmic evolution might be missing. Not all anomalies are created equal, though. While the Great Attractor and Shapley dominate their regions, other curiosities defy explanation even more boldly. There's the cold spot in the cosmic microwave background, a eerie, billion-light-year-wide patch of space suspiciously colder than its surroundings. Some speculate it could be a bruise from a collision with another universe, a wild idea that remains unproven. Then there's dark flow, the perplexing observation that certain galaxy clusters seem to be moving in the same direction at baffling speeds, as if tugged by something beyond our observable horizon. These phenomena don't just challenge our maps of the universe, they threaten to redraw them entirely. What ties these mysteries together is their defiance of expectation. The Great Attractor, Shapley, and their cosmic kin remind us that the universe is messier, more dynamic, and far less predictable than our textbooks suggest. Every time we think we've grasped the rules, gravity throws a curveball, revealing structures vaster and forces stranger than we imagined. And that's the thrill of it all. These anomalies aren't glitches in the matrix. They're clues pointing toward deeper layers of cosmic truth waiting to be uncovered. The more we study them, the clearer it becomes our universe isn't just expanding. It's alive with motion, a grand symphony of matter and energy playing out on scales almost too large to comprehend. Even as we grapple with the Great Attractor's pull, there's something stranger lurking at the edge of our cosmic maps, a phenomenon so baffling it's been dubbed dark flow. Picture this, not just individual galaxies, but entire clusters of them, thousands of them, all moving in the same direction at speeds that defy logic, as if swept up in a current we can't see. This isn't just a gentle drift, it's a coordinated rush toward some unseen horizon, a motion that can't be explained by the gravity of anything within our observable universe. If the Great Attractor is a whirlpool, dark flow is the entire ocean tilting, carrying everything with it. The discovery came from studying the cosmic microwave background, the faint glow left over from the Big Bang. Scientists noticed something odd. The light from these galaxy clusters showed subtle shifts, as if they were being tugged toward a point billions of light years beyond where we can see. Normally, the universe's expansion should scatter galaxies evenly in all directions, like raisins in rising bread. But dark flow suggests some raisins are rolling toward the same edge of the pan, hinting at something massive outside our cosmic oven. Something so enormous its gravity reaches across unfathomable distances to stir the universe itself. What could possibly exert such influence? One radical theory suggests it might be the gravitational pull of another universe beyond our own, a neighbor in the multiverse brushing against our cosmic bubble. Others propose it's evidence of a supercluster, a structure so vast it makes Laniakea look like a backyard garden. But here's the catch. According to our current understanding of cosmology, nothing should exist beyond the observable universe that could affect us. The expansion of space ought to make that impossible. Dark flow throws a wrench into the works, forcing us to question whether we've underestimated gravity's reach or missed a fundamental piece of the cosmic puzzle. The implications are staggering. If dark flow is real and after years of scrutiny, the data still holds up, it means the universe isn't just expanding, it's being shaped by forces we can't yet fathom. Imagine standing on a beach, feeling the tide pull at your feet, but instead of the moon, the tide is being driven by something invisible beyond the horizon. That's the scale of the mystery we're facing. It challenges the very idea of cosmic equilibrium, suggesting that even on the grandest scales, the universe is anything but uniform. Yet for all its strangeness, dark flow fits a pattern we've seen before. Just as the Great Attractor revealed hidden structures in our cosmic neighborhood, dark flow hints at an even larger architecture, a hierarchy of gravity stretching beyond our sight. Each discovery peels back another layer, revealing how little we truly understand about the forces sculpting the cosmos. And that's the real thrill. The universe, it seems, is always one step ahead, hiding its grandest designs just out of view. The sheer scale of the Great Attractor's mass is almost incomprehensible, so vast that it warps the very fabric of space-time around it. Current estimates suggest this cosmic heavyweight packs the equivalent of anywhere from 10,000 to 50,000 Milky Ways into a region just a few 100 million light-years across. To put that into perspective, imagine squeezing every star, planet, and speck of dust from our entire galaxy, then repeating that process thousands of times over, compressing all that matter into a single gravitational powerhouse. That's the kind of density we're dealing with here, but how do astronomers even begin to measure something this massive, especially when much of it is hidden behind the Milky Way's dusty veil? The answer lies in a phenomenon called gravitational lensing, one of Einstein's most astonishing predictions. When light from distant galaxies passes near the Great Attractor, its immense gravity bends the light's path, acting like a cosmic magnifying glass. By studying how these background galaxies appear distorted, stretched into arcs, or smeared into multiple images, scientists can map the attractor's invisible mass, much like tracing the outline of a shadow to guess the shape of the object casting it. What makes this measurement even more mind-bending is the realization that most of the Great Attractor's mass isn't even visible. The stars and galaxies we can see account for less than 10% of its total gravitational pull. The rest, it's the unseen hand of dark matter, the universe's most elusive ingredient, weaving an invisible scaffold that holds the entire structure together. Think of it like an iceberg. The luminous galaxies are just the tip, while the vast hidden bulk beneath the surface does the real work of steering cosmic motion. This leads to another startling comparison. The Great Attractor isn't just massive, it's unusually massive. Even for a supercluster, its gravitational influence seems disproportionate, as if the universe packed extra weight into this corner of space. Some researchers speculate that it might be the result of multiple superclusters colliding and merging over billions of years, a cosmic traffic jam where streams of galaxies and dark matter piled up into a single overwhelming knot. Others wonder if there's something even deeper at play, a flaw in our understanding of gravity itself that makes the attractor's pull seem stronger than our models predict. Yet for all its enormity, the Great Attractor isn't the universe's ultimate heavyweight. That title might go to the Shapley Supercluster, a behemoth nearly 8 times more massive. But here's the twist: the Great Attractor's influence isn't just about raw mass. Its location almost directly in our cosmic backyard gives it outsized sway over the motion of our local universe. It's like living downstream from a dam. Even if there are bigger reservoirs out there, the one closest to you shapes the current you feel the most. The more we learn about the Great Attractor's mass, the clearer it becomes that this isn't just an academic curiosity. It's a key piece of the puzzle in understanding how the universe organizes itself on the grandest scales. Every measurement, every lensed galaxy, peels back another layer of this enigma, revealing just how much we still have to learn about the forces sculpting our cosmic home. And with each discovery, one question lingers: what other hidden giants are out there, quietly pulling the strings of the universe? The cosmic microwave background isn't just a static snapshot of the early universe, it's a dynamic record, etched with the fingerprints of everything that's happened since the Big Bang. This faint afterglow, the oldest light we can see, carries subtle distortions, tiny ripples in temperature that tell a story about the universe's structure. And nestled within those ripples is the gravitational signature of the Great Attractor, bending the CMB's light like a thumb pressing into soft clay. Here's how it works. As the CMB's photons travel across the cosmos for over 13 billion years, they pass through massive structures like the Great Attractor. These colossal concentrations of matter, both seen and unseen, warp spacetime itself, creating gravitational wells so deep they subtly alter the photon's paths. This effect, known as the integrated Sachs-Wolf effect, leaves a telltale imprint on the CMB's temperature map. Hot spots and cold spots appear where photons gain or lose energy climbing in and out of these gravitational valleys, revealing the hidden architecture of the universe. When astronomers first mapped these distortions, they noticed something peculiar: a broad, diffuse region where the CMB's temperature dipped slightly, as if something massive had tugged at the light on its way to us. That something turned out to be the Great Attractor, its gravity subtly shifting the CMB's pattern like a magnet warping iron filings. It's a ghostly fingerprint, detectable only with instruments sensitive enough to measure temperature variations of a few millionths of a degree. Missions like WMAP and Planck, designed to study the CMB in unprecedented detail, became accidental detectives, uncovering the attractor's influence where optical telescopes saw only emptiness. But the CMB doesn't just confirm the Great Attractor's existence, it helps us weigh it. By analyzing the size and depth of these temperature distortions, scientists can estimate the total mass required to create them. The numbers are staggering. The attractor's gravitational reach suggests it contains tens of thousands of galaxies, along with vast reservoirs of dark matter, all packed into a region of space smaller than we'd expect for something so powerful. This mismatch between size and strength is part of what makes the attractor so enigmatic. It's as if the universe crammed a cathedral's worth of mass into a closet, defying our expectations of how matter should be distributed. The CMB also reveals how the attractor fits into the larger cosmic web. Those same temperature fluctuations trace the outlines of filaments and voids, the sprawling network of dark matter and galaxies that stretches across the observable universe. The attractor sits at a crossroads in this web, a gravitational nexus where multiple threads converge. Like a mountain at the center of a river basin, it draws everything toward it, shaping the flow of galaxies on scales we're only beginning to map. What's remarkable is that these CMB clues exist at all. The light we're seeing began its journey when the universe was just 380,000 years old, long before the Great Attractor took shape. That means these distortions aren't just showing us a snapshot of the early cosmos. They're documenting its evolution, capturing how gravity sculpted matter over billions of years into the structures we see today. The CMB isn't just a relic, it's a time machine, revealing how the universe grew from a nearly uniform soup of particles into the intricate tapestry of clusters and superclusters we call home. Yet for all it reveals, the CMB also deepens the mystery. Some of the temperature patterns around the attractor don't quite match our models, hinting that there's more to this region than we've accounted for. Could there be additional hidden mass, or perhaps something stranger, like a flaw in our understanding of gravity itself? Every answer the CMB provides seems to raise new questions, reminding us that the universe's biggest puzzles are often written in its faintest light. Right now, the Milky Way is racing toward the Great Attractor at over 1 million miles per hour, a speed that sounds impossibly fast until you remember the distances involved. Even at this velocity, it would take tens of billions of years to reach our mysterious destination. That's longer than the current age of the universe itself. So what does this mean for our galaxy's future? The answer lies in a cosmic dance where gravity, expansion, and time intertwine in ways that defy simple intuition. First, consider this. By the time we approach the Great Attractor, the Milky Way as we know it may no longer exist. In roughly 4 billion years, our galaxy is set to collide with Andromeda, its nearest spiral neighbor. The merger will reshape both galaxies into a single, elliptical behemoth often nicknamed Milkdromeda, scrambling star systems and birthing new stars in chaotic bursts. By then, our Sun will have already swelled into a red giant, likely engulfing Earth. So while the Great Attractor pulls Milkdromeda forward, any remnants of humanity, if they still exist, won't be witnessing the journey from this pale blue dot. They'll be watching from starships or megastructures, their perspective spanning millennia rather than lifetimes. But here's the twist: the universe's expansion complicates everything. As space itself stretches, the Great Attractor isn't standing still. It's being pushed outward by dark energy's relentless force. This creates a cosmic chase where our galaxy is hurtling toward a target that's simultaneously moving away. Current models suggest we'll never actually arrive in a traditional sense. Instead, the Milky Way will asymptotically approach the attractor's gravitational influence like a moth forever circling a distant flame. Over time, as expansion accelerates, the attractor's pull will weaken, leaving our galaxy adrift in an ever-darkening cosmos. Yet even this bleak future holds intrigue. During its long migration, Milkdromeda won't travel alone. The entire local group, a collection of 54 galaxies bound to us by gravity, will move in tandem, a celestial caravan flowing toward the attractor. Some of these galaxies, like the Triangulum Galaxy, might merge with us along the way, adding fresh stars and chaos to the mix. Others will trail behind, their own paths subtly bent by the attractor's reach. And all the while, new structures will form in the universe's ever-shifting web, some perhaps even rivaling the attractor's scale. For hypothetical future civilizations, this journey would unfold in slow motion. The constellations outside their windows wouldn't just shift over centuries, they'd dissolve entirely, replaced by unfamiliar skies as the galaxy pivots toward Centaurus. The attractor itself, now visible in full glory as the Milky Way's dust clears, might reveal even grander secrets: clusters of galaxies orbiting it like planets around a star, or filaments of dark matter glowing with the energy of colliding particles. But the ultimate irony: by the time we're close enough to study the attractor up close, the universe's expansion may have already carried its most distant treasures beyond our horizon forever. The cosmos giveth and the cosmos taketh away. What remains is the certainty that gravity's tug is relentless, the universe's scale is humbling, and our place within it, however fleeting, is part of a story written in the motion of galaxies. While the Great Attractor's gravitational pull seems undeniable, not all scientists are convinced it's a single, distinct structure. Some argue what we're seeing might not be a cosmic anomaly at all, just the expected clumping of dark matter on a grand scale. According to this view, the motion of galaxies toward this region could simply be the result of ordinary large-scale structure formation, where dark matter naturally pools into dense knots, pulling galaxies along for the ride. Imagine tossing a handful of pebbles into a pond. The ripples will intersect and create temporary patterns, but there's no single attractor, causing them, just the collective effect of many small splashes. Could the Great Attractor be a similar illusion, a statistical fluctuation magnified by our limited perspective? This skepticism isn't without merit. Simulations of cosmic structure formation consistently show that dark matter, under the influence of gravity, should form intricate webs of filaments and nodes. In this framework, the Great Attractor isn't a unique outlier but just one of many such nodes, albeit a particularly massive one in the universe's sprawling dark matter scaffold. The galaxies streaming toward it might simply be tracing the contours of this invisible architecture, no different from water following the path of least resistance down a slope. If true, labeling this region as a singular attractor could be misleading, implying a centralized force where none exists. Yet there's a counter-argument. The Great Attractor's gravitational influence seems unusually concentrated, even for a dark matter node. Most superclusters distribute their mass more diffusely, but the velocities of galaxies in this region suggest something denser, more focused. It's the difference between a sprawling suburb and a packed city center. Both contain people, but the intensity of movement in the latter hints at a stronger gravitational anchor. This discrepancy has led some researchers to propose hybrid models where the Great Attractor is indeed a dark matter hotspot, but one amplified by the chance alignment of multiple filaments, like rivers merging into a single powerful current. Then there's the puzzle of our own motion. The Milky Way's velocity toward the attractor is slightly faster than standard dark matter models predict, as if something extra is giving us a gravitational nudge. Could there be unseen mass, like a hidden cluster of galaxies, lurking in the zone of avoidance? Or does this mismatch hint at deeper gaps in our understanding of dark matter's behavior? Some theorists speculate that dark matter might interact in ways we haven't accounted for, perhaps through weak forces beyond gravity, adding complexity to the cosmic tug-of-war. The debate reveals a broader truth about cosmology. What we see in the universe often depends on how we choose to interpret the data. The Great Attractor could be a distinct structure, a statistical fluke, or something in between. What's certain is that this mystery won't be solved by better maps alone. It'll require peeling back the layers of dark matter's secrets, uncovering whether the universe's hidden scaffolding is as predictable as we think, or if it still holds surprises vast enough to redirect entire galaxies. The Great Attractor's enigmatic pull hasn't just fascinated scientists, it's ignited the imaginations of storytellers, weaving its way into books, films, and even video games as a symbol of the universe's untamed mysteries. Take the three-body problem, Liu Cixin's groundbreaking sci-fi series, where the attractor becomes a haunting backdrop for humanity's struggle against cosmic forces beyond comprehension. Or Destiny, the blockbuster video game franchise, which recasts it as a malevolent entity called the Darkness, a gravitational god lurking in the void. These creative interpretations tap into something primal, the terror and awe of being drawn toward something unseen, something powerful, with no certainty of what waits on the other side. What makes the attractor such fertile ground for fiction? It's the perfect blend of real-world science and tantalizing ambiguity. Unlike black holes or alien invasions, which sci-fi has explored exhaustively, the attractor remains just obscure enough to feel fresh. Writers can project their wildest theories onto it, a cosmic prison, a gateway to another dimension, even the physical manifestation of a higher intelligence. In Alastair Reynolds' Revelation space novels, it's reimagined as the hideout of an ancient, paranoid civilization that fled there to escape detection. The attractor's impenetrability becomes its allure because science hasn't fully decoded it. Artistry rushes in to fill the gaps. Filmmakers love it for the same reason. The concept of an invisible, unstoppable force pulling everything toward an uncertain fate is cinematic gold. It's no accident that the climax of Interstellar, with its haunting depiction of higher dimensional beings manipulating gravity, resonates so deeply with the attractor's real-life mystique. Both play on humanity's fear of being helpless in the cosmos, a speck caught in currents we can't control. Even when not named directly, the attractor's influence echoes through stories like Event Horizon or Sunshine, where voyages into the unknown become metaphors for confronting the limits of human understanding. But pop culture's fascination isn't just about fear, it's also about wonder. The attractor represents one of the last great cosmic mysteries, a reminder that even in an age of hyper-detailed simulations and deep space probes, the universe still holds puzzles too big for our tools to solve. That duality, both menace and majesty, fuels its appeal. Whether framed as a threat or a revelation, it taps into our deepest questions. Are we alone? What lies beyond the horizon? And if the universe is pulling us somewhere, will we recognize what we find when we get there? Perhaps the most telling detail is how rarely these stories offer definitive answers. The attractor's power lies in its mystery, its refusal to be pinned down. Just as scientists grapple with conflicting data, storytellers let it remain shrouded, a blank canvas for our collective curiosity. That's why it endures both in labs and in legends, not despite the uncertainty, but because of it. The Great Attractor isn't just a destination, it's a mirror reflecting back our endless hunger to explore the unknown. The journey toward the Great Attractor isn't a peaceful cruise through space, it's a chaotic, high-speed collision course where galaxies jostle and merge in a gravitational free-for-all. Imagine a crowded highway where every vehicle is hurtling toward the same exit at millions of miles per hour. But the exit keeps moving, and the cars are entire galaxies, each weighing billions of suns. That's the kind of chaos unfolding as the Great Attractor's gravity orchestrates a cosmic demolition derby on a scale almost too vast to comprehend. Galactic collisions aren't rare in the universe, they're inevitable. Gravity ensures that over enough time, every galaxy will interact, merge, or be torn apart by its neighbors. But near the Great Attractor, this process accelerates. The sheer density of galaxies in this region turns it into a gravitational blender, where spiral galaxies like our own Milky Way are stripped of their delicate arms, twisted into elliptical blobs, or devoured entirely by larger neighbors. The Hubble Space Telescope has captured stunning snapshots of this violence elsewhere in the universe. The antennae galaxies, locked in a slow-motion collision that's sparking frenzied bursts of new star formation, or the mice galaxies, their long tails of stars stretched like taffy by tidal forces. These are previews of what awaits galaxies caught in the attractor's pull. Yet the outcome isn't always destruction, sometimes it's transformation. When two galaxies merge, their stars rarely collide outright. The distances between them are too vast. Instead, their gravitational dance reshapes both galaxies into something new. Picture two crowds of people merging in a plaza. While individuals might weave around one another, the group as a whole becomes denser, more chaotic. Over billions of years, spiral galaxies like the Milky Way and Andromeda will lose their elegant disks, becoming featureless ellipticals, galactic retirees with little gas left to birth new stars. The Great Attractor's region may already be littered with these cosmic relics, the remains of earlier mergers that burned through their star-forming fuel in violent bursts of activity. But speed matters. The faster galaxies plunge toward the attractor, the more violent the collisions. Simulations suggest some galaxies could be flung past one another like cosmic pinballs, their trajectories bent by close encounters into unpredictable arcs. Others might be funneled into dense clusters where they're harassed by repeated gravitational nudges, a process astronomers call galaxy harassment. Over time, these interactions strip away gas and dust, leaving behind gaunt skeletons of stars. The most massive galaxies act as bullies, growing larger by cannibalizing their smaller neighbors in a process known as hierarchical merging. By the time the Milky Way arrives, the attractor's core could be dominated by a handful of these supergalaxies, each the product of thousands of mergers. Yet amidst the chaos, there's beauty. Collisions trigger starbursts, episodes of frantic star formation as gas clouds compress and ignite. The resulting newborn stars paint merging galaxies in brilliant blues, their light outshining everything else for millions of years. The Great Attractor's realm might resemble a celestial fireworks display, with galaxies flaring and fading as they collide, but these bursts are short-lived. Eventually, the gas runs out and the fireworks stop, leaving behind galaxies that are redder, quieter, and far less lively than their spiral ancestors. What does this mean for the Milky Way? Our galaxy's fate is already sealed in one sense. The coming merger with Andromeda will reshape us long before we reach the attractor's heart. But beyond that, the journey could grow even wilder. If we're funneled into a dense cluster, tidal forces might stretch the Milky Way into a streamer of stars, a process called spaghettification on cosmic scales. Alternatively, we could become a satellite of a far larger galaxy, orbiting it like a moon around a planet, our identity gradually erased. The irony is that by the time we're close enough to witness the attractor's full spectacle, the universe itself might be fading. Dark energy's accelerating expansion could rip future observers' view of distant galaxies away, leaving only the attractor's core visible in an otherwise empty sky. The grand collision course we're on now might end in isolation, a final act written not with a bang but with a slow, silent dimming. Yet for now, the chaos ahead reminds us that the universe is anything but static. It's a living, evolving arena where gravity writes the rules and galaxies are merely players in its vast, unpredictable game. While the Great Attractor pulls galaxies toward it with immense gravity, there's another player in this cosmic tug-of-war, one that doesn't pull but pushes. Meet the dipole repeller, a sprawling void so empty, its absence of mass might actually be shoving galaxies across the universe. Picture a game of interstellar pinball where the Great Attractor is the target and the dipole repeller is the flipper, launching entire galactic clusters in its direction. This isn't just a theoretical curiosity, it's a crucial piece of the puzzle explaining why galaxies move the way they do. The concept of a repeller flips our intuition about gravity on its head. Normally, we think of mass as the only thing that matters: planets, stars, and galaxies pulling on each other. But voids, regions of space nearly devoid of matter, create a different kind of influence. Imagine standing in a crowded room where everyone suddenly steps back from you. You don't move, but the space around you expands, creating the illusion that you're being pushed forward. That's essentially how the dipole repeller works. Its emptiness, stretching over hundreds of millions of light years, means there's less gravity holding nearby galaxies in place compared to the denser regions surrounding it. The result, galaxies aren't just pulled toward the Great Attractor, they're also pushed away from the repeller like marbles rolling downhill from a peak of nothingness. Scientists first proposed the dipole repeller's existence when they noticed something odd about the Milky Way's motion. Even after accounting for the Great Attractor's pull, our galaxy's velocity didn't quite match predictions. There had to be another force at play, something counterbalancing the attractor's grip. By mapping the distribution of galaxies and voids, researchers pinpointed a colossal underdense region in the opposite direction of the attractor, a cosmic desert where matter is eerily scarce. This void, the dipole repeller, isn't just empty by chance. It's one of the largest known structures of its kind, a bubble of near-nothingness whose gravitational push helps explain the precise speed and direction of our galaxy's journey. What makes the repeller so fascinating is how it reshapes our understanding of cosmic dynamics. We're used to thinking of gravity as a force of attraction, but on the largest scales, absence can be just as powerful. The universe isn't just a collection of massive objects, it's a patchwork of dense clusters and vast voids, each playing a role in the grand ballet of motion. The Great Attractor and the dipole repeller are two sides of the same coin, their opposing influences creating the delicate balance that shapes the flow of galaxies. Yet studying the repeller is even harder than probing the Great Attractor. While the attractor hides behind dust, the repeller hides behind nothing, literally. Telescopes rely on light to map the cosmos, but a void emits none. Instead, scientists infer its presence by what's not there, the unusual motion of galaxies that can't be explained by visible matter alone. It's like deducting the shape of a shadow by watching how objects move around it. Recent surveys, like the Cosmic Flows Project, have traced these galactic currents in unprecedented detail, revealing the repeller's ghostly outline in the patterns of cosmic drift. The interplay between the attractor and the repeller hints at a deeper truth about the universe. It's not just expanding uniformly, but flowing in intricate, large-scale currents. Galaxies aren't passive drifters, they're riders on these cosmic rivers, swept along by the combined push and pull of the universe's largest structures. And just as the attractor might be part of something bigger like Laniakea, the repeller could be one of many such voids shaping the cosmos's architecture. So the next time you look up at the night sky, remember, the stars aren't just being pulled toward a hidden giant. They're also being nudged along by the silent, empty spaces, the great cosmic nothings that, in their own way, hold just as much sway over our fate as the brightest galaxies. The universe, it seems, is full of surprises, even in its emptiest corners. At the smallest scales of the universe, space isn't smooth. It's a bubbling, frothing sea of quantum foam, where particles wink in and out of existence in a dance governed by the laws of quantum mechanics. These fleeting fluctuations might seem insignificant, but what if they're the hidden threads weaving the fabric of gravity itself? Some physicists speculate that the same quantum chaos shaping the subatomic world could scale up to influence cosmic giants like the Great Attractor, creating gravitational anomalies that bend the paths of galaxies. The idea hinges on a radical rethink of gravity's nature. Einstein's general relativity describes gravity as the curvature of spacetime by mass, planets, stars, and galaxies denting the cosmic fabric like weights on a trampoline. But at quantum scales, spacetime isn't rigid. It's a turbulent foam of virtual particles popping into and out of existence too quickly to measure directly. These fluctuations aren't just noise, they could subtly alter how gravity propagates across vast distances. Picture a calm pond disturbed not by a single stone, but by a ceaseless rain of tiny droplets. Over time, those ripples might add up to waves powerful enough to redirect entire galaxies. One provocative theory suggests that quantum foam could create gravitational hotspots, regions where random fluctuations accidentally align, amplifying gravity's pull in unpredictable ways. It's like rolling dice billions of times. Eventually, you'll get a streak where the same number keeps appearing. In the universe, these statistical flukes might concentrate gravity's force, forming invisible knots like the Great Attractor. If true, the attractor isn't just a cluster of dark matter. It's a quantum accident frozen on a cosmic scale, a place where microscopic chaos snowballed into a gravitational titan. But how could something so small affect something so vast? The answer might lie in entanglement, one of quantum mechanics' strangest phenomena. When particles become entangled, their properties remain linked no matter how far apart they are. Some theorists propose that spacetime itself could be entangled, with fluctuations in one region instantly influencing another. The Great Attractor, then, might not be pulling us directly. It could be entangled with vast patches of the universe, its gravity echoing across the cosmos through a web of invisible quantum connections. Critics argue this stretches quantum mechanics beyond its known limits. After all, quantum effects usually cancel out at larger scales, vanishing like ripples in a stormy ocean. Yet supporters counter that dark matter. The Great Attractor's hidden backbone might interact quantumly in ways we haven't detected. If dark matter particles exhibit quantum behavior, their fluctuations could propagate through the cosmic web, imprinting structures like the attractor on the universe. It's a long shot, but so was dark matter itself a century ago. The boldest theories go even further. If spacetime is fundamentally quantum, then the Great Attractor might not be a thing at all. It could be a glitch in the code of reality, a place where the universe's underlying quantum geometry folds back on itself. Think of it as a cosmic wrinkle, a gravitational scar left over from the Big Bang's quantum turbulence. In this view, the attractor isn't pulling galaxies, it's revealing where the fabric of spacetime is subtly frayed. Whether any of these ideas hold water remains to be seen, but they underscore a thrilling possibility. The universe's largest mysteries might be rooted in its smallest details. The Great Attractor isn't just a destination, it's a clue, a cosmic breadcrumb leading us toward a deeper understanding of how the quantum and the colossal intertwine. And that journey, much like the attractor itself, is pulling us into uncharted territory. When we think of cosmic forces powerful enough to bend entire galaxies off course, black holes are the obvious suspects, especially the supermassive ones lurking at the hearts of galaxies. These gravitational monsters, weighing millions or even billions of times the Sun's mass, dominate their surroundings with an irresistible pull. So could the Great Attractor's immense gravity come from a collection of these behemoths, their combined might warping space-time on an unprecedented scale? The idea isn't as far-fetched as it sounds. In fact, recent studies of galactic nuclei suggest that supermassive black holes might play a far greater role in large-scale cosmic structure than we ever imagined. Take the Milky Way's own supermassive black hole, Sagittarius A. While it's relatively quiet now, we know from other galaxies that these objects can unleash unimaginable energy when feeding on surrounding matter. Active galactic nuclei, or AN, spew out jets of radiation and particles powerful enough to influence gas across entire galaxy clusters. Now picture hundreds or thousands of these AGN packed into the Great Attractor's core, their combined gravity and energy output creating a gravitational nexus unlike anything in our local universe. Simulations show that in dense regions, black holes can indeed cluster, forming a sort of dark skeleton that guides the motion of galaxies around them. The Great Attractor could be the ultimate example of this phenomenon, a cosmic downtown where black holes are the high rises and everything else orbits at their whim. Yet there's a catch. Even an army of supermassive black holes wouldn't account for the attractor's total mass. While these objects are staggeringly dense, they're still just drops in the bucket compared to the dark matter halos enveloping galaxies. To explain the attractor's pull, we'd need black holes far more massive than any we've observed, or something even stranger. Some theorists propose a middle ground. What if the Great Attractor's core hosts a rare ultra-massive black hole, a relic from the early universe when conditions might have allowed such giants to form? These hypothetical monsters, with masses exceeding 100 billion suns, could anchor the entire region's gravity. We've never confirmed one exists, but if they do, the attractor would be the perfect hiding place. The smoking gun might lie in the strange behavior of galaxies near the attractor's heart. Observations reveal unusually high velocities and distorted shapes, telltale signs of extreme gravitational forces. Some galaxies show evidence of past AGN outbursts, as if their central black holes were stirred up by close encounters with something massive. Others stream toward the core in tight, fast-moving filaments, a pattern that suggests an invisible anchor. If supermassive black holes are the culprits, their gravitational waves, ripples in space-time from collisions, should eventually be detectable by observatories like LIGO and the upcoming LISA mission. Finding such signals would be like hearing the distant echoes of the attractor's hidden engines. But here's the twist. Even if black holes contribute to the attractor's pull, they're likely just part of a larger puzzle. The real power might come from how they interact with dark matter. Some models suggest black holes could act as seeds, their gravity helping to concentrate dark matter into denser knots. Over billions of years, this feedback loop would amplify their influence, turning a group of black holes into the gravitational powerhouse we see today. It's a cosmic snowball effect where small initial differences grow into titanic structures. The deeper we look, the clearer it becomes that the Great Attractor defies simple explanations. Supermassive black holes might be players in this drama, but they're not the sole directors. Like searching for a conductor in an orchestra of shadows, we're left piecing together clues, each revelation bringing us closer to understanding how the universe's most mysterious forces intertwine. And if black holes are indeed part of the answer, they're reminding us that even in the darkest corners of space, the smallest things can have the biggest pull. The universe is caught in a tug of war between two opposing destinies, one pulling us toward an unfathomable end, the other toward an enigmatic center. On the grandest scale, the cosmos is marching toward heat death, a slow fade into darkness where all energy disperses, stars burn out, and matter itself decays into a featureless void. Yet here we are, hurtling toward the Great Attractor at breakneck speed, as if nature has carved out an exception to the rule. These two forces, one relentless expansion, the other an inexorable pull, paint a paradoxical picture of our cosmic fate, revealing how the universe's story isn't written in a single stroke, but in layers of contradiction. Heat death is the ultimate triumph of entropy, the universe's inevitable slide into equilibrium. Imagine a cup of coffee left untouched for eternity. Eventually, it cools to room temperature, its energy dissipated beyond recovery. Now scale that up to galaxies, galaxy clusters, and beyond. Over trillions of years, star formation will sputter out, black holes will evaporate, and the cosmic microwave background will redshift into oblivion, leaving a cold, silent expanse. This isn't just theory, it's the logical endpoint of everything we know about thermodynamics and expansion. The universe, in essence, is running down like a clock with no one to wind it back up. Yet against this bleak backdrop, the Great Attractor stands as a defiant anomaly. While the universe expands, this gravitational titan bends the rules, pulling galaxies into its orbit like a whirlpool resisting the outgoing tide. It's a reminder that on local scales, gravity still writes the script, weaving structure into the cosmos even as dark energy stretches it apart. The attractor's influence is so potent that within its sphere, the rules of cosmic evolution are rewritten. Galaxies collide, merge, and ignite with new stars, defying the universe's broader trend toward stillness. In this corner of existence, the story isn't about dispersion. It's about convergence, a fleeting defiance of the inevitable. The tension between these fates reveals a deeper truth. The universe doesn't have a single destiny, but many. Heat death may be the final chapter, but along the way, gravity carves out pockets of drama, places where matter resists the void for a little longer. The Great Attractor is one such pocket, a gravitational oasis where the usual rules of expansion take a backseat. It's as if the universe, knowing its ultimate fate, allows itself moments of rebellion, regions where the dance of galaxies continues even as the music fades. What's fascinating is how these forces interact. Dark energy drives the universe apart, but gravity, especially on scales as vast as the attractors, can still create local eddies of order. Over time, though, even these will be overwhelmed. As expansion accelerates, the attractor's pull will weaken, its influence stretching thinner against the cosmic tide. The galaxies it once held close will drift apart, their shared journey fading into the growing dark. It's a reminder that no structure, no matter how massive, is immune to the universe's grand design. The irony is sublime. Even as we race toward the attractor, we're also part of a much larger current, one that leads only to stillness. These dual trajectories, one a fiery rush toward collision, the other a slow freeze into oblivion, frame our existence in a cosmos of contrast. For now, gravity's drama holds our attention, but the final act belongs to entropy. The Great Attractor is just a subplot in a much longer story. A reminder that even in the face of an inevitable end, the universe still has moments of breathtaking spectacle. And for those of us watching, that's enough to make the journey unforgettable. Dr. Karen Masters still remembers the night she first glimpsed the Great Attractor's fingerprints in the data. It was 2 in the morning at the Arecibo Observatory, and I was mapping hydrogen emissions from galaxies behind the Milky Way's dust, she recounts. Suddenly, the velocities made no sense. Entire clusters were moving sideways, as if something massive was yanking them off course. That something, of course, was the attractor, its gravity warping galactic motions like a magnet bending iron filings. Masters' experience mirrors countless astronomers' stories, moments of bafflement giving way to revelation, all while wrestling with a cosmic enigma half obscured by our own galaxy. For Dr. René Cron-Courtoueg, dubbed the Great Attractor Hunter, the challenge has always been the Zone of Avoidance, the thick band of Milky Way dust blocking our view. Imagine studying a mountain range while standing in a blizzard, she explains. Her team pioneered radio surveys to pierce through this veil, uncovering hundreds of hidden galaxies. One discovery still haunts her. We found a galaxy cluster twice as massive as expected, sitting right where models predicted the attractor's core should be. It was like stumbling upon a buried city, yet even now, she admits, we've only sketched the outlines. The heart of the attractor remains shy, hiding just beyond our sightlines. The human side of this quest often gets overlooked. Dr. Yehuda Hoffman remembers the skepticism when his team proposed the Great Attractor's motion might itself be driven by an even larger structure. Colleagues called it cosmic heresy. He laughs. That structure, now known as the Shapley Supercluster, turned out to be real, but Hoffman's work revealed a deeper truth. The universe loves hierarchies. Every time we find a gravitational giant, there's usually something bigger pulling the strings. His simulations suggest the attractor is just one node in a web of flows stretching across the observable universe. Then there's the technology problem. Dr. Martha Haynes describes upgrading the Green Bank telescope's receivers to detect faint hydrogen signals from attractor region galaxies. We'd wait weeks for clear skies, only to have a thunderstorm wipe out our data, she says. But persistence paid off. Her team recently mapped peculiar velocities across the region, revealing how the attractor's pull varies with distance. The biggest surprise, some galaxies are moving faster than our models predict. It's as if the attractor has help, maybe more dark matter or something we haven't accounted for. For younger astronomers like Dr. Michelle Kluver, the attractor represents both opportunity and frustration. Using infrared data from the Spitzer Space Telescope, she's traced galaxy flows with unprecedented precision. Every breakthrough comes with 10 new questions, she admits, one lingering mystery. Why do some galaxies resist the attractor's pull? There are rebels in every crowd, even in space. Her work hints that local interactions, galactic collisions, supermassive black hole activity might occasionally override the larger flow. These researchers share a common thread, moments of awe when confronting the attractor's scale. Dr. Brent Tully, who co-discovered the Laniakea Supercluster, recalls the first time he visualized the attractor's gravitational basin, seeing thousands of galaxies streaming toward this invisible point. It felt like discovering a continental divide, but for the cosmos. Yet he's quick to add humility. We're like ants mapping currents in a river. The real story is far bigger than our tools can show. The attractor's hold on astronomy isn't just scientific, it's deeply personal. Dr. Daniel Pomed, who 3D mapped the galaxy flows around the attractor, describes sleepless nights wrestling with supercomputer outputs. There's a thrill when the numbers finally click, when you realize you're seeing something no human has ever witnessed. His colleague, Dr. Helene Courtois, puts it poetically, the attractor isn't just pulling galaxies. It's pulling us, our curiosity, our stubbornness, our need to understand. In chasing it, we're really chasing our place in the universe. What emerges from these voices isn't just data, but a portrait of science in action, messy, exhilarating, and deeply human. The Great Attractor may be a cosmic mystery, but solving it, or failing to, rests on late nights at remote observatories, heated debates at conferences, and the quiet determination to keep looking up, even when the universe refuses to give up its secrets easily. As Cron Courtueg puts it, every time we answer one question, the attractor throws us another, and that's exactly why we can't look away. Ever tried spotting the Great Attractor in the night sky? Here's the catch: you can't, not directly at least, hidden behind the thick star fields of our own Milky Way. It's like trying to see a distant mountain through a snowstorm. But that doesn't mean amateur astronomers are left in the dark. With a little ingenuity, you can trace the attractor's gravitational fingerprints right from your backyard, using tools as simple as a star chart and as powerful as public data from NASA telescopes. Start with the stars you can see, grab a detailed sky map, or better yet, an app like Stellarium. and look toward the constellation Centaurus. That's where the attractor lurks, just beyond the Milky Way's dusty plain. While you won't spot the attractor itself, you can observe the motion of galaxies around it. Take a pair of binoculars or a small telescope and scan for bright galaxies like Centaurus A, a massive elliptical galaxy caught in the attractor's pull. Notice how it sits along a river of other galaxies, all flowing toward the same invisible point. It's like watching leaves swirl in a stream. You can't see the current, but their motion betrays its presence. For a deeper dive, explore public data from space telescopes. Platforms like NASA Skyview let anyone pull up infrared and radio observations that pierce through the Milky Way's dust. Search for hydrogen emissions, a telltale sign of galaxies hidden behind our cosmic blind spot. Overlay these with velocity maps from projects like Cosmic Flows, and suddenly the attractor's influence becomes visible. You'll see galaxies racing toward Centaurus at speeds that defy the universe's expansion, their paths bent like compass needles pointing to a magnetic north we can't see. Want to contribute to real science? Join citizen astronomy projects like Galaxy Zoo, where volunteers help classify galaxies in attractor region surveys. By cataloging shapes and colors, you might uncover galaxies overlooked by algorithms, clues to the attractor's hidden structure, or analyze data from the Dark Energy Survey, where amateurs have helped spot peculiar galaxy motions hinting at even larger gravitational anomalies. The thrill here isn't just in observing, it's in connecting the dots. Every galaxy you map, every velocity you track, stitches another thread into the attractor's invisible tapestry. And who knows, with enough eyes on the data, the next breakthrough might come not from a mountaintop observatory, but from your living room. After all, the universe's greatest mysteries aren't just for professionals. They're for anyone willing to look up and through the cosmic veil. Even after decades of study, the Great Attractor remains one of astronomy's most stubborn puzzles, a cosmic riddle wrapped in dust, obscured by distance, and tangled in gravitational contradictions. At the heart of the mystery lies a simple yet profound question. What exactly is this thing? We know it's massive, tens of thousands of galaxies worth of mass concentrated in a relatively small pocket of space. But the details, those are maddeningly vague. Is it a single, dense supercluster or a chance alignment of multiple structures that merely look like a unified object from our vantage point? Current maps suggest the latter, but without a clear view of its core, we're left guessing. Every new observation seems to add another layer of complexity, like an onion with no center. Then there's the dark matter problem. The Great Attractor's gravitational grip is far stronger than the visible matter we've detected can explain. This isn't unusual in cosmology. Dark matter outnumbers ordinary matter 6-1, but the attractor's ratios are extreme. Some regions appear to have too much gravity, as if dark matter is clumped there in ways our models don't predict. Could there be an unknown type of dark matter, something that interacts differently with itself or with galaxies? Or is this a sign that gravity itself behaves strangely on such vast scales, bending the rules Einstein gave us? The attractor isn't just hiding its composition, it's challenging the foundations of physics. Perhaps the most tantalizing question is whether the attractor is merely a waypoint in an even grander journey. Recent studies reveal our entire supercluster, Laniakea, is itself in motion, pulled toward the Shapley Supercluster, a gravitational titan 8 times more massive than the attractor. This raises a dizzying possibility. What if the attractor is just one link in a chain of cosmic giants, each pulling the next in a hierarchy we've only begun to trace? It's like discovering a mountain range only to realize it's part of a continent, and the continent is adrift on an even larger tectonic plate. Where does it end? Some theorists speculate there could be structures so vast they span billions of light years, their gravity shaping the universe in ways we can't yet imagine. And what about the anomalies? Galaxies near the attractor's supposed core move at speeds that defy expectations, as if whipped by an unseen force. A few even seem to be moving against the flow, like salmon swimming upstream. Are these outliers evidence of chaotic interactions, or could they hint at something stranger, like quantum fluctuations playing out on cosmic scales, or relics from the universe's violent infancy? The attractor's unpredictability suggests we're missing a key piece of the puzzle, something that could rewrite our understanding of how large-scale structure forms. The greatest frustration and the greatest thrill is how little we truly know. Every answered question spawns three more, each more perplexing than the last. The attractor isn't just a destination for galaxies. It's a mirror reflecting back how much of the universe remains wild, uncharted, and utterly mysterious. And in that uncertainty lies the real magic, the chance to keep discovering, to keep reaching for answers just beyond our grasp. After all, the best mysteries aren't meant to be solved quickly. They're meant to pull us deeper. The next generation of space telescopes is gearing up to peel back the Great Attractor's secrets like never before. And leading the charge is the European Space Agency's Euclid mission, set to create the most detailed 3D map of the universe's dark matter skeleton. Unlike traditional telescopes that focus on stars and galaxies, Euclid's cutting-edge optics are fine-tuned to detect the invisible gravitational fingerprints dark matter leaves behind. By surveying billions of galaxies across 10 billion light-years, it will trace how their light bends around unseen mass concentrations, effectively turning the entire cosmos into a colossal dark matter detector. For the Great Attractor, this could be revolutionary. Imagine finally seeing the contours of the monster that's been pulling us, its hidden arms of dark matter, its gravitational peaks and valleys laid bare for the first time. But Euclid isn't working alone. NASA's upcoming Nancy Grace Roman Space Telescope, launching later this decade, will complement these efforts with an even wider field of view, scanning vast swaths of sky to pinpoint how dark matter distorts the shapes of distant galaxies. Together, these missions could solve one of the attractor's biggest riddles: why its gravitational pull seems stronger than the visible matter we've detected. If dark matter is clumped in unexpected ways around the attractor, or if entirely new physics is at play, Roman's ultra-precise measurements might catch the discrepancy. It's like putting the universe on a scale, and the Great Attractor's weight just doesn't match the visible ingredients in the recipe. On the ground, new radio telescopes like the Square Kilometre Array SCAR will add another layer to the hunt. With thousands of antennas spread across 2 continents, SKA will map hydrogen gas in galaxies behind the Milky Way's dust curtain, piercing the zone of avoidance that's long obscured the attractor's core. Early tests have already revealed ghostly galaxies lurking in this blind spot, and full operations could uncover the missing mass that's been hiding in plain sight. Combined with space-based data, this might finally answer whether the attractor is a single dense knot of galaxies or a sprawling intersection of cosmic filaments. The most tantalizing possibility: these missions could reveal if the Great Attractor is moving itself. Gravitational waves, ripples in space-time from colliding black holes or other cataclysms might hold clues. Future detectors like LISA, a space-based gravitational wave observatory, could sense if the attractor's core hosts violent mergers, hinting at the unseen giants powering its pull. Meanwhile, advanced simulations running on next-gen supercomputers will test wilder theories, like whether quantum fluctuations or higher dimensions could amplify gravity in this region. What's at stake isn't just a better map, it's a chance to rewrite cosmic rulebooks. If these missions confirm the attractor defies standard models, we might need a new understanding of dark matter, gravity, or even the universe's structure. Or perhaps the biggest surprise will be realizing the attractor isn't unique, that similar anomalies dot the cosmos, unseen until now. Either way, the era of guessing is ending. Soon, we'll see the invisible hand that's been steering our galaxy for billions of years, and finally learn what's been pulling us into the unknown. The Great Attractor isn't just bending the paths of galaxies, it's tugging at something deeper, something intrinsically human, our unshakable need to seek meaning in the cosmos. For millennia, we've looked to the stars not just to map the heavens, but to find our place within them. The idea that we're being pulled toward an unseen destination resonates far beyond astronomy. It mirrors the very essence of curiosity, that gravitational force within us that compels exploration, discovery, and the relentless pursuit of answers. What if the universe, in its infinite mystery, is reflecting back our own yearning to be part of something grander? Consider how civilizations have long woven narratives around celestial motion. Ancient cultures saw comets as omens, planets as gods, and constellations as stories etched in light. Today, we replace myth with science, dark matter instead of deities, redshift instead of prophecies, but the impulse remains unchanged. The Great Attractor, invisible yet undeniable, becomes a modern symbol of that same existential pull. It's the cosmic equivalent of a question mark hanging in the void, inviting us to chase it. And chase it we do, building ever larger telescopes, launching probes, and peering through the Milky Way's dust, all to satisfy a hunger as old as consciousness itself. There's a poignant irony here. The attractor's pull is indifferent, a brute fact of physics. Yet in our interpretation of it, we can't help but anthropomorphize to ascribe a kind of intentionality. We speak of galaxies racing or streaming toward it, verbs that imply purpose. This isn't just poetic license, it's a window into how humans cope with the universe's vast indifference. By framing natural phenomena as journeys with destinations, we make the cosmos feel less alien, more navigable. The attractor then becomes more than a mass concentration. It's a narrative anchor, a way to storyboard the chaos of cosmic motion into something that feels like it has direction. Philosophers have wrestled with this tension for centuries. Does the universe inherently possess meaning, or do we impose it through observation and metaphor? The Great Attractor sits at the heart of this debate. On one hand, its existence is a cold, calculable reality, a node in the cosmic web where gravity overrides expansion. On the other, its very invisibility, its refusal to be fully known, transforms it into a mirror for our existential musings. It's no accident that the attractor's discovery coincided with humanity's growing awareness of its own fragility in an expanding, entropic universe. Here was proof that even the mightiest galaxies aren't truly adrift, they're caught in currents vaster than themselves. That realization is equal parts comforting and unsettling, a reminder that we're part of a story much bigger, one whose plot we're still deciphering. Science fiction often explores this duality. In films like Contact or novels like Solaris, encounters with the unknown serve as proxies for humanity's quest for meaning. The Great Attractor, had it been known earlier, would have fit seamlessly into these tales, a literal manifestation of the call to adventure that defines so many heroic journeys. But unlike fiction, there's no guarantee of revelation waiting at the attractor's core. It might just be a particularly dense patch of dark matter with no deeper significance. And yet, the act of searching itself, the missions planned, the papers written, the late nights at observatories becomes its own kind of meaning-making. Perhaps that's the ultimate lesson the attractor offers, not that the universe is pulling us toward answers, but that the act of pursuit is itself the answer. Every measurement taken, every galaxy mapped, is a testament to our refusal to accept the void as empty of significance. The attractor's gravity shapes galaxies, our curiosity shapes our understanding of it. In this dance between the physical and the philosophical, we find a paradox. The more we learn about the cosmos, the more we uncover about ourselves, and that, in the end, might be the most profound pull of all. Imagine if humanity built a starship capable of crossing the vast gulf to the Great Attractor. Would you board it? Picture this: a vessel traveling at near light speed, taking tens of thousands of years to reach a destination where galaxies collide like cosmic bumper cars, where spacetime itself bends under the weight of invisible mass. Would the chance to witness the universe's hidden architecture first and be worth the one-way journey? Or does the sheer scale of such a voyage, longer than all of human civilization, make it feel less like exploration and more like surrendering to the void? Here's another thought experiment. If we could see the Great Attractor clearly, unobscured by the Milky Way's dust, what do you think it would look like? A swirling vortex of galaxies packed so tightly they blend into a haze of starlight, or something stranger, a dark, geometric lattice of filaments with black holes humming at the intersections like nodes in a grand cosmic circuit. Scientists can simulate it, but the reality might defy even our wildest visualizations. And let's talk about that pull, the force dragging our galaxy toward something unseen. Does it unsettle you knowing we're caught in a current we can't escape? Or is there something comforting about it, like being carried along by a river whose destination, though unknown, is part of a larger, inevitable flow? For some, it's a reminder of how small we are. For others, proof that even in an expanding universe, nothing is truly adrift. Now here's the real kicker. If the Great Attractor is just one link in a chain of even larger structures, each pulling the next, where does it end? Could there be a final attractor of attractors, some ultimate gravitational anchor at the edge of existence? Or is the cosmos an endless series of nested currents with no center, just motion within motion? The answer might not just redefine our place in the universe, it could rewrite the laws of physics itself. So what's your take? Drop your thoughts in the comments, whether it's your dream cosmic road trip, a theory about what's really lurking in the attractor's core, or even your favorite sci-fi take on it. After all, the best thing about mysteries isn't just solving them, it's sharing the wonder they spark along the way. The Great Attractor remains one of the universe's most humbling enigmas, a hidden gravitational giant that defies our view yet bends the paths of galaxies, including our own, with irresistible force. We've chased its shadow through radio waves and infrared light, mapped its influence on the cosmic microwave background, and even glimpsed the superclusters it anchors. Yet for all our tools and theories, its core stays shrouded, a reminder that the cosmos keeps its deepest secrets just out of reach. Standing here on a speck of rock orbiting an ordinary star, it's astonishing to realize that we've deduced so much about a force we can't even see directly. That's the power of curiosity. The human drive to decode the universe whispers into something resembling understanding. What's striking isn't just the scale of the mystery, but our willingness to confront it. The Great Attractor doesn't care that we exist. Its gravity would pull just the same if Earth had never formed. Yet here we are, stitching together clues from distorted starlight and galactic velocities, piecing together a puzzle that spans hundreds of millions of light years. There's something poetic in that asymmetry, a force vast enough to redirect galaxies, noticed and measured by creatures living on a mote of dust. It's as if the universe built a labyrinth and then whispered, "Go on, try to find the center." This dance between the knowable and the unreachable is what makes astronomy so thrilling. Every answer, whether it's the attractor's connection to dark matter or its role in the Laniakea Supercluster, unlocks new questions. Maybe that's the real lesson. The universe isn't a puzzle to be solved, but a conversation to be joined. Each discovery, from the first anomalous galaxy motions in the 1970s to tomorrow's Euclid telescope data, is another sentence in a story with no final page. So what's next? The Great Attractor won't reveal itself overnight, but the tools we're building, next-gen telescopes, gravitational wave detectors, AI-driven simulations, are refining our questions as much as they're sharpening our answers. And that's the beauty of science. It's not just about arriving at truths, but about learning how to ask better questions along the way. Whether the attractor turns out to be a dark matter anomaly, a quantum fluke, or something beyond our current physics, the pursuit itself reshapes how we see our place in the cosmos. As we wrap up this cosmic journey, remember, you're part of the story too. Every time you look up at the night sky or dive into a mystery like this, you're adding to humanity's collective wonder. The universe is vast, yes, but it's also connected, and so are we. If you've enjoyed unraveling the Great Attractor with me, hit that subscribe button and ring the bell. There are plenty more cosmic riddles ahead. After all, the next big discovery might be just one observation away, and I'd love for you to be here when it happens. Until then, stay curious, keep looking up, and never stop asking what if. The universe is listening.